Okay. This is lecture 26 of condensed matter physics 1. And what we are going to do today is further our discussion from lecture 25, where we had talked about vibrations in a crystal with monatomic basis. So, today's lecture we are going to include one more atom, and we are going to talk about vibrations in a crystal with basis. That means there are more than one atoms at a lattice point, and this gives to something called optical modes. So, let us see what happens if I have a system where instead of one atom at a site, I have two of them. So, let me make the picture for one atom, and that was like this, with springs like force in between, and we had considered nearest neighbors. Now, I am going to consider a system where I have these atoms along with another atom at each site, and they are both connected with this spring kind of thing. So, essentially a force which is proportional to linear displacement, and I am going to call one particular site the jth site. That is, I have the jth lattice point there. The next one is j plus 1 at site, and the previous one is j minus 1 at site, and all the spring coefficients I am going to take the same C, but what is happening here is that my unit at each lattice site is this whole thing. All the springs are the same. So, this is again we are making a model where we assume number 1 only nearest neighbor interaction, just like we did in the monatomic case, and the force is proportional to displacement. But this will bring out all essential features of what we want to learn. This can be solved analytically. The real calculations are more complicated, but all the general features that come out in that are roughly the same. So, let us see what can happen in this case. Just to give you an example, suppose I had a large mass and a small mass connected. And it is suppose connected to a wall by a spring. If I take this whole thing as a unit, one motion that is possible is this whole thing, this unit moves back and forth as 1. So, this whole thing is moving back and forth. No displacement, relative displacement between the two masses. The other possibility is that this mass and the other mass, they perform relative motion. With this spring roughly being out of action. So, in this case Cm is at rest, and there is in the previous case no relative motion, and Cm is moving. And the frequencies of the two are very different. This you have worked in your classical mechanics or basic mechanics course, and we are going to see something similar here. So, in the monatomic case, what we had was when we plotted omega versus k, we had a dispersion like this. This is omega, this is k, and at k equals 0, there was this linear relationship between omega and k. Omega was V sound times k, and we call these acoustic modes because Vs is the velocity of sound. This really represents the longitudinal mode in this represents sound propagating in the system. However, what we are going to see, if there is only relative motion between the two atoms, then even at 0 k there might be a finite frequency, and that is what is going to emerge, and we are going to call this optical mode, and I will tell you why. So, let us develop this model now. So, what I am going to consider is that I have these atoms with a different mass than the other one. Let me make one more out here. And I am going to call the displacement of the red atom V, displacement of the green atom U, and they are all connected by this spring. And this model, I am going to take all the spring constants to be the same. The distance between the sides is A, and let us say this one is jth lattice point. The next one is going to be j plus 1. The previous one is going to be j minus 1, and I am considering interaction only between these three. So, this is the nearest neighbor interaction. So, let us write the equation of motion for each one of them. I am going to have the mass for the bigger one m1 and the smaller one m2. So, everything is now known. So, if I write the equation for the bigger mass, I am going to have m1 uj double dot, that is the acceleration, is equal to the force on the jth u mass is going to be due to this the mass m2 on the right and mass m2 on the left. So, I am going to have C Vj minus Uj plus C Vj minus 1 minus Uj. Slightly different from what we had in the monatomic case. So, this I can write as C Vj plus Vj plus 1 minus 2 Uj. That is my equation number 1, and that is for U. For the other mass, I am going to have m2 V j double dot is equal to, again taking nearest neighbor interaction, C u j plus 1 minus V j plus C u j minus V j. You can check that all the directions are correct. So, let me just write that, check that all force directions are correct. And that is my equation number 2. So, I have now two equations, right. Let me write it properly. I have m 2 V j double dot is equal to C u j plus 1 plus u j minus 2 V j. That is my equation number 2. Two equations to be solved for 2 u j and V j. Again you notice that these equations look like wave equations if you go to continuum limit. So, let me write that. These are like wave equations in the continuum limit. And therefore, we are going to again take the solution like wave like solution. Let us do that now. So, let me write the equations first. I have m u j double dot is equal to m 1 is equal to C V j plus V j minus 1 minus 2 u j, equation 1, and I have m 2 V j double dot is equal to C u j plus 1 plus u j minus 2 V j, equation number 2. I am going to assume a solution now for u j as a function of time is going to be some amplitude u e raised to I k j a minus omega t, and for v j t is equal to v e raised to I k j a minus omega t, and substitute. When I substitute, the first equation is going to be minus omega square u m 1. Let me write in the correct order. M 1 u e raised to all this with k j. I am just writing the relevant terms, is equal to C v e raised to I k j a plus v e raised to I k j minus 1 a minus 2 u e raised to I k j a, and then e raised to minus I omega t cancels. And therefore, the equation that I get is minus omega square m 1 u is equal to e raised to I k j a would cancel. I get C v plus v e raised to minus I k a minus 2 u. You bring all the u's and v's together, you get minus omega square m 1 plus 2 c u minus c 1 plus e raised to minus I k a v is equal to 0. That is my equation 1. You do the same thing for the second equation and you are going to get C. We write it in red since I have been following red for that. I am going to get C 1 plus e raised to I k a u minus omega square m 2 plus 2 c v is equal to 0. That is my equation 2. So, I have gotten two equations for two unknowns u and v. Now, if I want u and v to be not equal to 0, then the determinant of the equation should vanish, and therefore, I should have for non-trivial solution the condition minus omega square m 1 plus 2 c minus c 1 plus e raised to minus I k a then I would have C 1 plus e raised to I k a, and out here I will have minus omega square m 2 plus 2 c, determinant is equal to 0. Okay. So, let us write this again. I have determinant of minus omega square m 1 plus 2 c minus 1 plus e raised to minus I k a c 1 plus e raised to I k a c minus omega square m 2 plus 2 c, determinant is equal to 0, and that should give you omega. Let us write these equations. So, I have minus omega raised to 4 m 1 m 2 plus that will be minus omega square m 1 plus m 2 times 2 c plus 4 c square minus plus c square 1 plus 1 plus 2 cosine k a is equal to 0. That is the equation you get. So, this can be rewritten as omega raised to 4 m 1 m 2, I will bring it to the right hand side, minus omega square m 1 plus m 2 times, here is a 2 and c, plus 4 c square minus 2 c square 1 plus cosine 2 cosine k a. Is equal to 0. Simplify it further. So, I get omega raised to 4 m 1 m 2 minus 2 m 1 plus m 2 c omega square plus 2 c square 1 minus cosine of k a is equal to 0. And therefore, the solution is going to be omega square is equal to 2 m 1 plus m 2 c plus minus square root of 4 m 1 plus m 2 whole square c square minus 8 C square m1 m2 1 minus cosine of K A divided by 2 m1 m2. You simplify it further and keep going further, and what you are going to get is that omega square is going to be coming to be m1 plus m2 C plus or minus C square root of m1 plus m2 whole square minus 4 m1 m2 sine square K A by 2 divided by m1 m2. That is the answer. So, you are going to get 2 omega for each k, right. So, that is the first thing you notice, 2 values of omega for each k. That is number 1. Number 2, let us take k equals 0, that is the center of the Brillouin zone. Then I get omega square equals m1 plus m2 C plus minus sine square k is going to be 0. So, I get m1 plus m2 C divided by m1 m2. So, 1 omega square is 0, and the second omega square is 2 C m1 plus m2 divided by m1 m2. You immediately recognize this is the reduced mass inverse for the two masses. So, this is equal to 2 C over mu reduced. So, there are two different omegas, and if I were to plot it or show it on this k versus omega k versus omega graph, at k equals 0, I have two values, one right here and the other one right here. This value is 2 C m1 plus m2 divided by m1 m2 square root. So, there is a non-zero frequency, which is, since there is a reduced mass coming in, you can see that this is going to be relative motion, which I will show in a few minutes. But right now immediately you realize by looking at it and from the experience of dealing with two masses, that whenever there is a reduced mass coming, this is due to the interaction between the particles. So, this could be that. Let us also find out what is the frequency at the Brillouin zone boundary. So, let us also take K A equals pi. In that case, omega square comes out to be m1 plus m2 C plus minus m1 minus m2 C divided by m1 m2. So, in this case, omega 1 square is equal to 2 C divided by m2, and omega 2 square is equal to 2 C divided by m1. So, what you have, if you were to make this picture again, at k equals 0, I had one point here, and at the Brillouin zone boundary pi by a, or at minus pi by a, because adding or subtracting 2 pi by a does not make a difference. I have frequency, let us assume m1 is greater than m2. So, I have a frequency which is smaller here and another frequency which is larger. This value is 2c over m1, and this value is 2c over m2. And if you connect them, this is acoustic mode, it goes like this, and this one will go something like this. On this side, I will have something like this and something like this. This is known as optical mode. So, what you have, if I plot it slightly bigger, is that in the basis you have pi by a minus pi by a, and one mode like this and the other mode like this. This is optical, this is acoustic. Acoustic reason is clear, because for long wavelength this is linear with slope being speed of sound, and I will tell you in a minute why the other one is called optical mode. But the big thing is that in optical mode, omega k equals 0 is not equal to 0. That is number 1. Number 2, optical mode has hardly any dispersion. That means omega k is roughly, I am not saying perfectly, but roughly a constant, does not change much. Okay, now let us explore it further. Relative motion of masses in acoustic and optical mode. So, let us go back to the equations for this. What are the equations that I had? I had minus omega square m1 plus 2c minus c 1 plus e raised to minus I k a. This was u v equals 0. And the other equation for relative motion, I do not really have to worry about the second equation. Nonetheless, for completeness, let me write this. And the other one was c 1 plus e raised to minus I k a u minus omega square m2 plus 2 c v is equal to 0. And we are talking about k equals 0. What happens at k equals 0? I have omega 1 equals 0 and omega 2 equals the square root of 2 c m1 plus m2 over m1 m2. If I substitute this either in equation 1 or equation 2 for omega 1 equals 0, what do you have? You have 2 c u minus 2 c v is equal to 0, and this gives you u equals v. So, near k equals 0, the displacements of two atoms are roughly the same. So, what you have is here are these atoms and here are the other atoms forming a basis. Since u and v are the same, there is no relative motion. This whole unit shifts by the same amount. The amount may change depending on the wavelength, but they shift by the same amount. So, the motion of the entire unit is together. The motion of entire basis is together for acoustic mode. What about the other omega? For the other omega, for omega 2, which is equal to omega 2 square equals 2 c m 1 plus m 2 over m 1 m 2. You have minus 2 c m 1 plus m 2 divided by m 2 u minus 2 c v is equal to 0, and that gives you minus 2 c m 1 over m 2 u. Let us see, there was a plus 2 c u also here, plus 2 c u. That cancels. So, this minus 2 c v is equal to 0, or m 1 u plus m 2 v is equal to 0. Let us see what does that mean. So, given this, lattice, this one is u, this one is v. For the optical mode, I have m 1 u plus m 2 v is equal to 0, and this implies C m is at rest. It does not move, it remains at x equals 0. So, if you look at this motion, and I will make it bigger, if I look at this atom and this atom, their motion is such that if this guy is moving this way, this fellow is moving this way. And the distances, let me make the arrows corresponding distances are going to be relatively like this, so that this fellow remains at 0. Number 2, I have m 1 over m 2 equals minus v over u, and that I have shown by this displacement. So, if I look at the lattice, what do I see? I see that in the optical mode or in the acoustic mode, this whole unit is shifting together. So, it is going back and forth. So, this motion is like monatomic lattice. On the other hand, what you have in the other one, let us make 3 of them. The motion is right here. They are moving with respect to each other. It is as if this link does not matter. And that is why it is not the omega versus k curve is flat, because there is no kind of traveling wave. Omega is almost flat, and this is the frequency of their relative motion. Of m 1 and m 2. And when would that happen? That would happen if you have a positive, a negative, a positive, a negative ion, and if I apply a field, electric field say in this direction, then this fellow would move in the direction of the field, the negative charge will move in the opposite direction, and if this E field arises from EM wave or light, then they are going to perform this motion. Light symbolically, I mean frequency could be quite different, but this is what it does, and that is why this is known as optical mode. This can be excited by electromagnetic fields in a ionic lattice. The other one gives you sound, and that is why that is a acoustic mode. Now that you understood this, let me ask you a question. If M1 equals M2, then the lattice becomes monatomic. In that case, how come there is an optical mode? That is one question I want you to think about, because you will still have, if you do this calculation, you will still have this one mode which has omega equals non-zero at k equals 0, and the structure would be similar. So, how come there is an optical mode, whereas we had seen earlier there is no optical mode? Now, the other thing I want you to give is work out the relative displacements of atoms for k equals pi over a, that is at the Brillouin zone boundary. Now, what we had seen earlier when doing monatomic lattice, that in monatomic lattice there were longitudinal and transverse acoustic modes. Question is, will that happen for optical modes too? The answer is certainly yes. So, what is happening is, you have these atoms, and we have considered motion to be along k. The motion could also be transverse. So, motion could be like this, or could be perpendicular to the sheet. Those will be transverse modes. So, in general, what you are going to have is acoustic modes which are longitudinal and acoustic modes which are transverse. Notice that I am making frequency of transverse modes to be slightly smaller than the longitudinal modes. That is because the transverse stiffness may not be that much. And then you are going to have the optical modes and longitudinal optical is usually slightly less frequency than transverse optical. So, all kinds of modes exist in these lattices, and we have done analysis through a model and we have gotten some general features which are going to be true in general. Details may vary when you do an exact calculation. Again, I am going to ask you two questions. One question is, how will one determine the omega k versus k curve experimentally? I want you to think about it. And the other question I want to leave you with is, for which branch of vibrations, that is optical or acoustic, will Einstein or Debye model for calculation of CV apply? This is the other question I want you to think about. So, I have given you a general feeling about what happens when you have a lattice or a crystal with a basis. In that case, you get two branches, longitudinal, the acoustic and the optical branches, and both branches have longitudinal as well as transverse motion associated with them. So, with this, let me conclude the lecture. That we have obtained omega k versus k curves, basically what is known as dispersion relation for crystal with a basis, and two, a new mode optical mode of vibrations arises in this case. This is in addition to the acoustic mode, and third, optical mode omega is hardly dependent on k. So, dispersion is very little. Thank you.